Is it working? In Zoom? Okay. All right. Good morning, everyone. I think it's time to start. First, maybe have. Oh, sorry. I need to use this microphone. Hello. 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 Seems doesn't work. Hello. 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 It works. Looks like. Anyway, I try to increase my voice. So first of all, you might have seen the reminder of the final exam. We're gonna have our final exam online because of the health and safety issue. I think it might be too risky to bring everyone in person here, even this classroom is pretty big. Right, so we're gonna have it online on Canvas, but our schedule will be follow the schedule given by the campus. It will be on Wednesday, December 15th from 8 a.m. to 10 a.m. So don't forget, don't get up late, miss that. Otherwise, if you're gonna miss that time window, you will not be able to access that online exam. So just be sure to mark a calendar for that. We'll keep reminding you about this schedule. And the second thing is that, again, please start doing the last homework right now. Otherwise, because everyone has, I guess you guys now only take one class, right? You might have like multiple classes. So don't try to rush for everything until like 3 days, right? And regarding the final exam, it's just open book. There's no like computation requirement or ask you to prove anything. It's just a conceptual test, meaning that as long as you are kind of understand what we have discussed throughout the semester, that'll be good. We won't ask you to like calculate something like calculate information gain or majority error or Gini index in front of your computer screen. That's not our goal, because you have done that in your homework assignment. We don't want to repeat that. So, but we do encourage you to go through the slides we have discussed throughout semester, and be sure you understand the content of the slides, because it's open book, right? The best reference will be your slides, and we'll do that. You might need to, look into which specific things or definition in your slides. You need to ensure yourself are able to identify those content quickly. Right? Okay, any question regarding the no. We're gonna spend like 15 or 20 minutes in the last lecture to briefly walk through what we have discussed so far. But given the difficulty of the final exam, I mean, it's not hard at all, actually. So we don't think it's necessary to have an actual practical exam, practice exam. Other question regarding the final exam schedule? Okay, great. So in the last lecture, we talked about the idea or concept called Bayesian learning, right? So Bayesian learning, we introduced like two notions of Bayesian learning. One notion is that, okay, I'm gonna learn some probability function rather than some deterministic labeling function, right? So if you, in the traditional classification task, where my task is to map each input instance to either 1 or -1, right? But if you switch to probabilistic learning, we're gonna define our target function as mapping from the input to some chance or some probability between 0 and 1. So instead of learning to directly predict the label, we're gonna learn to predict the probability your label is 1, right? We're learning to predict the chance, not to predict the label directly. So there are a lot of like implications there, because in practice, we not only want some like deterministic prediction, like 1 or -1, we also want some chance. We want to give some confidence estimate of your label. Yeah, that's important. We have discussed that in the last lecture. And the second notion is about the second notion of Bayesian learning is about how do we search the hypothesis space, right? So we know in general every learning algorithm essentially to search over the hypothesis space, right? This search is guided by the training data, right? And then we want to identify which particular hypothesis we believe is the best, right? So under this kind of idea, we have defined the loss minimization principle, right? We define some loss over the training set and then minimize the loss to find the best hypothesis, right? But in Bayesian world, we're gonna define the best hypothesis as the one who, given the training data, is most likely to be the true hypothesis. So basically, we give some probabilistic meaning about the searching procedure, right? And then to do that, we need to assign some, prior distribution over the hypothesis space, right? You might encode your prior, your own preferences, your own experience, your beliefs about which type of hypothesis were more likely to be true, which are less likely, right? And then you have to define, given each specific hypothesis, suppose that hypothesis is the true hypothesis, what is the likelihood this hypothesis will generate the observation or generate the training data, right? And then by combining the prior and the likelihood, we can infer the posterior probability for each hypothesis, if it is true or not, given the training data, right? So that's the Bayesian interpretation or Bayesian formulation of the learning procedure. And that's the two notions in Bayesian learning. And then we talk about what is MAP estimation and what is MLE estimation, right? Maximum A posterior estimation, maximum likelihood estimation. Maximum A posterior estimation wants to find the parameter or hypothesis which can maximize the posterior probability, right? So we're gonna see that this specific instance in today's lecture, right? It is proportional to the prior multiplying with likelihood, right? But if you just ignore the prior, or in other words, you assume that the prior is simply uniform, you believe every hypothesis has an equal chance to be the true hypothesis before we see any data, right? You don't put any uneven beliefs, and then you only maximize the likelihood, right? This is called maximum likelihood estimation, right? So today, we're going to talk about an instance of Bayesian learning, which is called logistic regression. right? So the logistic regression is belongs to the first notion of Bayesian learning, meaning that we want to learn a mapping from the input to some chance, not just the label, right? The chance of being label one, right? So, but we're gonna still introduce how do we estimate, how do we learn that under both the MAP principle and the MLE principle, right? Maximum a posterior estimation and maximum likelihood estimation. Right? So before we introduce what is logistic regression, right? Let us look at what we have seen so far, right? Where are we? So we have seen the following ideas, right? So we have discussed quite a few linear models, right? We have discussed nonlinear models, right? So we actually have two ways to build up nonlinear models. One is to extend linear models, say with feature mapping or kernel trick. Right? We also can build up nonlinear models from scratch, like neural networks, right? So you have if you're currently doing homework 5, you know that neural networks is built from scratch, right? It's not completely based upon linear models, right? And then when we carry out the learning, we're going to use the so-called loss minimization principle, right? In other words, it's called empirical risk minimization principle. Right? We're going to review this later, right, and then say how it is connected to the Bayesian learning, right? And to avoid the overfitting issue, we can introduce some regularizer in our loss, which we call this idea as regularized empirical risk minimization, right? So what is the example of this? Can anyone point out some example for some instance of regularized empirical risk minimization? Yeah, exactly right. The typical example will be SVM. Remember, in SVM, we introduce a regularization term, right? It's half of the square norm of the weight factor, which implies we want large margins, right? Large margin means you want small VC dimension, we want to penalize the hypothesis space which are over complicated, right? So for logistic regression, we'll say our objective is to learn a probability mapping, right? The output is between 0 and 1, which I have emphasized, right? And we'll also say how we conduct the Bayesian learning criterion to estimate the parameters in logistic regression. Okay, here's our outline, right? We're gonna first introduce the model definition for logistic regression, right? How do we define a hypothesis which maps any input vector to a probability between 0 and 1, right? And then we'll talk about how do we conduct training, right? And then we're going to use map estimation and MLE estimation. And finally, we're going to link back to the learning paradigm we used before, namely the loss minimization. We're going to review their tight connections. It's actually very interesting. Okay, so first, let us look at the definition of logistic regression. Right? So first, here is the setup. So our goal is to conduct binary classification. Again, is to do binary classification. Is to do classification. It's not like regress your example to arbitrary continuous numbers. Okay. So the inputs, without loss of generality, we can assume they are feature vectors in a d-dimensional space. And the labels are either -1 or 1. So we have exactly the same setting as the binary classification problem we discussed before, right? And also we assume our training data are pairs of xi and yi, meaning that we got input feature vectors and output binary labels -1 or +1. Right? And suppose we have collected M training examples. Right? So although our training outputs are either -1 or 1, meaning discrete, but the goal of the logistic regression is not to predict your label is 1 or -1. Instead, we try to predict the probability that given your input, your label is 1. So that means the probability, that means your output of logistic regression classifier could be 0.6, meaning that you have a 60% of chance to label X as positive, or like 0.2, meaning that you only have a 20% chance to label your instance as negative. Right? So that's our goal, right? We want to learn a mapping between X and this probability. Right? So this is a key difference from the previous problem we have discussed, right? The original problem is to map your feature vector to either -1 or 1, all right? Now we have a modified problem. We want to map some continuous number right between 0 and 1, right? It won't be bigger than 1, it won't be less than 0. Otherwise, the number won't be a valid probability, right? So that's why it's called a logistic regression, because we're going to still predict a continuous number, but we restrict the range of numbers between 0 and 1. Right? So now I want to ask, if you want to design such kind of regressor, right? What kind of hypothesis would you like to choose? Any thought? Can we use linear model? Can we use linear regression? Just give me a guess. Can we define our hypothesis or just the linear regression function like W transpose X? No? Why? Yeah, exactly right. That's the key. Right? We actually have like a strict restriction to the output space, right? We want that for any hypothesis you choose, well, the output must be between 0 and 1. Otherwise, it's not a valid probability. Right? So you have to ensure that the output of your hypothesis to be between 0 and 1. So that's why we cannot use kind of arbitrary continuous function, right? Like linear regression won't be possible. Neural network won't be possible. Right? But there are still many hypothesis spaces available, right? And here, in logistic regression, we're going to focus on a specific type of hypothesis, right? Which is called logistic function, right? Or sigmoid function. So you can see that the sigmoid function is the one right now you're using to implement neural network, right? But then we're going to take a closer look at this sigmoid function and say which the property does it have, right? So we define our hypothesis for logistic regression as a sigmoid function, and the input of sigmoid is a linear function. So it's still kind of linear model, because we're going to first do some linear regression, and then we throw this regression result into the sigmoid to get our final output. So for convenience, right? Again, we're gonna simplify the notations, meaning that X here is augmented with some constant feature 1, so that the weight factor actually includes the original feature vector W and the Boss parameter B, right? So this is actually the same notation sugar as we used in linear regression and linear classification. And then we throw this inner product into our sigmoid function. So the sigmoid function has this form, right? So this is a reasonable choice. But I want to ask, why is this a reasonable choice? What's the range of the sigmoid function? Yeah, it is exactly between 0 and 1, right? So you can see that it's interesting. No matter how large or how small your input, like let us look at the general form. Suppose your input of sigmoid is just z, right? So it's 1 plus 1 plus e to the power of minus z, right? So even if your z goes to infinity, this exponential term will be 0, right? So the sigmoid is 1, right? If z goes to minus infinity, what will happen? It goes to minus infinity, so minus z will be infinity, right? So take exp over to the power of infinity, it gives infinity in the denominator, right? So 1 over some infinity is 0, right? So you can see that it can guarantee your output of sigmoid is between 0 and 1. Right? That's what we require, because we require our hypothesis to ensure you predict a valid probability. Right? So if we take a look at the curve of the sigmoid function, right, it looks like this. Right? So z is the axis, right? So you can see that how the y value, y-axis, which is actually the sigmoid function output, varies along with the input z, right? So this is a monotonic function, obviously, and this can also be shown like algebraically by taking the derivative. We have shown how to take the derivative of that. It's simply sigmoid z times 1 minus sigmoid z, right? We have done that when we talk about the neural network, right? I'll recommend you to review that if you forgot, right? But anyway, you can show that the derivative or the gradient of sigmoid is always non-negative. That's why this function is monotonically increasing, right? So you can see that the smaller the z value you have, the smaller the sigmoid function value, right? So, but the minimum value it can go to is just 0. And on the other hand, if you increase z, right, the larger z, the sigmoid function value is getting closer to 1. Right? And if z goes to infinity, the sigmoid z will go to 1. Okay? So that's how that is the property of the sigmoid function. So like one might ask, in addition to sigmoid function, do I have any other hypothesis have kind of a similar property, right? Between will always give the output between 0 and 1 and also monotonically increasing along with z? They're actually out. For example, if you instead of using sigmoid, you're using some CDF function of the continuous probability. Like remember, if you have some continuous random variable, like if you look at the CDF function, the cumulative density function, you know the integral of the cumulative density function from minus infinity to infinity must be 1, right? So you can define your hypothesis as some integral function, like from minus infinity to z. So this is another common use. One, if you specify the CDF to be like a Gaussian CDF, and then you're doing the so-called probability regression. probability regression. It's also a widely used model, especially for Bayesian people, like especially for guys like me. But here we're gonna only talk about the logistic regression, meaning that we use Sigmoid. So now I want to give kind of like a brief review. How do we calculate the derivative with respect to the input, right? So because you're gonna use them to implement your logistic regression, we got some homework problem which is optional to implement your logistic regression. I mean, it will be useful. Although it's if you want to implement, and also your homework, some manual problem requires you to calculate some derivatives and a stochastic gradient. So it's not bad to look at them again, right? So this is a sigmoid function. So if you want to take the derivative of sigmoid over the input, right? So it's something like that. We just follow the rule, right? So this is actually 1 plus e to the minus z to the power of -1, right? So if you're taking the derivative, you apply the chain rule, you're gonna take the square of the denominator, and then you put a minus sign in front of it and take this exp and take the derivative over this minus z inside, right? So you got a 2 minus sign, they're gonna cancel, right? So you got this, right? And then the k inside is that you're gonna write out this square. So one piece is just 1 over 1 plus e to the power of minus z, and the other piece will be exp to the minus z over 1 plus exp to the minus z, right? So if you divide the denominator and the numerator, you'll get that is essentially 1 minus the sigmoid. And then you see that, okay, this derivative is simply the sigmoid times 1 minus sigmoid. Right? This is very, very important, the trick to simplify the gradient calculation of the sigmoid function and also the objective of the sigmoid for the objective for the logistic regression model. Okay, any questions so far regarding the property and the property of the sigmoid function? Okay, great. Let's continue. So now, according to the logistic regression model, right? And we have modeled the probability. Your label is 1 given your input feature vector x, the model parameters, which are vector w, as a logistic function or sigmoid function of this w transpose x, right? So if you write it out, it's just 1 over 1 plus e to the power of minus w transpose x, right? So accordingly, if you want to calculate the probability, your y takes -1, which is to subtract 1 by your sigmoid function, right? Which is, 1 minus this guy. Well, it is straightforward to say it is e to the power of minus w transpose x over the same denominator, right? So we want to make a little bit simplification, right? So because we're having to put like exp terms on both numerator and denominator, that looks ugly. So I'm gonna divide both numerator and denominator by this exp, right? So it will give us this one, right? So this 1 over 1 plus e to the power of w transpose x. So now, by looking at this and this, can we try to unify the two probabilities with one formula? Yeah, but you should put a minus sign in front of it, right? So that's a commonly used trick, right? So no matter your y is 1 minus 1, I can always write down the probability your y takes that value as this, right? 1 over 1 plus e to the power minus y w transpose x, right? You can just check, right? So if y is 1, it gives the formula in the top, right? And if y equals to minus 1, it reduces to the second line, right? So that's a convenient expression, right? So we're going to use them in our likelihood and map estimation, right? You don't need to consider two cases like separately, and for each case you write a like piece of code to deal with that. That's really tedious and ugly, right? So after, suppose now we have defined our logistic regression model, right? And suppose now we have obtained our model parameters, and we know that our logistic regression model just gives us a probability, right? 0.6, 0.2, or 0.5, right? And then according to this probability, can we give some label prediction? Right? A commonly used heuristic will be, okay, if your prediction, this probability is bigger than half, is greater than half, we're going to predict the label to be 1. Otherwise, we're going to predict label to be a minus 1. That's reasonable, right? If my prediction tells me that the chance of labeling this example to be 1 is bigger than the chance of labeling that example to be minus 1, I'm gonna assign label 1, right? And vice versa, right? Like suppose my probability prediction is 0.8, meaning that I believe 80% chance this example should have label 1. Then if I have to give some label, I need to give 1, right? I need to choose the label which I'm most confident with, right? And on the other hand, if my prediction is 0.1, right? Meaning that it might only have like 10% chance to be label 1. I should assign, we should assign the label to be minus 1, right? Anyway, any question regarding the prediction rule with the logistic regression? Okay, so now let us contrast with our previous prediction rule. So in our previous prediction rule, if our linear classifier, we're going to just look at the sign of the prediction score, right? The score here is still W transpose X. If the W transpose X is bigger than 0, okay, we're going to predict label 1, right? Otherwise, we're going to predict label minus 1. So what's the relationship between our previous prediction rule and our logistic regression prediction rule? Any thought? Mm-hmm. Any other supplement?
Change 0 to 50%. If the number of the chance is bigger than 50%, predict 1. Before, if the number will be bigger than 0, predict 1.
Yes, exactly right. So in essence, I mean, the rules we used for logistic regression looks seemingly like different from the previous rule, but they are in essence are the same, right? So if you take a look at the logistic regression, right, when your probabilities will be bigger than half, it's only when it's a score bigger than 0, right? If this W transpose X is bigger than 0, well, it's not easy to show that this whole fraction will be bigger than 0.5, right? And it is consistent with that your sign is 1, right? Now, on the other hand, if your score is negative, like this fraction, this sigma function will give you less than 0.5, right? And you're going to predict as negative. And same time, because as simultaneously this sign is negative, our previous rule will give the negative prediction as well. Does it make sense? So essentially, these two rules are doing the same thing, at least in the prediction step. Right? Is everyone comfortable? We just want to point out the connection, right? But we have additional advantage of using logistic regression. Why? Because not only given some positive 1, -1 as a final prediction, we also know the probability or our confidence. Right? So I know I'm gonna predict this label as 1, but I also give you my confidence like 0.8. Right? So that confidence is important in many applications. We have covered in the last lecture. Right? Okay, any questions so far? This is all about the model definition and prediction rule with logistic regression. Yes.
Then we have like same benefit as
Yes, yes. Why what?
Why don't we do it? So you said that the only benefit of the situation to the linear what's the probability, right? So that in process of your so I would say like why bothering and then like not mapping the output of the linear to 0 and 1. It's 0 and 1. So that's not the same.
So you mean you can directly do some linear regression, and then if you want to get probability, you just take this sigmoid transform?
You can't get without the sign, just
well, in that case, well, I think your prediction accuracy, final prediction accuracy might not change, but your estimate of the probability itself can be problematic, right? Because you don't restrict your score, right? Like you give, maybe use your way of training, I'm gonna still give the correct prediction, but I won't be able to give a well-calibrated probability. Like it's supposed to be 0.8, but your prediction might give me 0.9 or 0.3, 0.6. So here, the logistic regression, the stress, it stresses on that we're gonna give some reasonable probability which can learn from data. It's a first priority is to learn the probability rather than give you the final discrete labels. Another question? Okay, great. So now let us look at the computational perspective, right? So how do we train a logistic regression classifier given a bunch of examples? We know that the examples are input and output pairs, but output pairs are not probabilities, but just 1 or -1, right? So of course we need to we need to define a proper objective function which can associate our prediction to the final discrete labels, right? So we're gonna first talk about the maximum likelihood estimation, and then we can easily extend to the maximum a posterior estimation by adding the priors. So to conduct maximal likelihood estimation, right? What we want is here. Right? So our model parameters for logistic regression is this weight vector, right? So the weight vector again is augmented weight vector, include the feature weight vector and the bias parameter B. So don't forget about that, right? And then given this M training examples, if we want to conduct MLE, it basically means I want to find this parameter vector which maximizes the likelihood of the data, right? And then we know our examples are drawn independently and identically distributed, right? And how do we proceed? We can first write down the joint probability of those M examples, because those examples are ID, right? So actually their joint likelihood is a product of their individual likelihoods, right? So we maximize this whole likelihood essentially is to maximize this product of the individual likelihood for each example, P of yi given xi and w, right? And as we discussed before, right, we don't want to deal with product of the probabilities. Why? Because each particular number is very small, like 0.0, 0.2, 0.1, 0.2, 0.15, 0.8, something like that, right? If you have 1,000 examples, you multiply them together, it's very easy to truncate to 0, right? So that will be very numerically unstable. So the idea will be maximize this in log domain, right? You take a logarithm over this product, and then you're maximizing a summation over the log likelihood of each training example, right? So remember, the log function is a monotonic increasing function. If you just append it to any objective function, it won't change the function optimal, right? So we maximize the log likelihood of those examples. Right? And by definition, right, we just mentioned before, this probability P of yi given xi and w is a sigmoid function of yi times w transpose xi. So now you can see the convenience, right? We use we unify the two cases, y is 1, y is 2, y is 1, y is -1 in one expression. That's very convenient. You don't need to separate it out into two cases, right? Just use one formula to express the likelihood, which is 1 over 1 plus e to the power of minus yi w transpose xi. You know, you just substitute back into this, right? We got our objective function, which is maximize w with respect to the summation. Each summation is minus logarithm 1 plus this, right? The minus sign comes from here, right? Because you take a logarithm over this. You take a logarithm over this, right? So you have this is actually the denominator take the power of -1, right? So you move it in front of logarithm. That's where the minus sign comes from here, right? Of course, this looks a little bit ugly, right? I don't want this minus sign in front of it. I can just change the maximization to be the minimization, right? This is they're equivalent. So we minimize this summation over M training examples, where each summation is this logarithm 1 plus e to the power of minus yi w transpose xi. So now we can see that how we do this maximal likelihood estimation. The goal is to maximize the likelihood of the probabilistic classifier under the logistic model, right? And then after several simple derivation, our goal becomes to minimizing a summation over the training example. So now this summation actually defines a loss over the training example. Right? So this loss is called a logistic loss. So now you can see the connection. Right? So maximize the likelihood for the logistic regression model, which is a Bayesian model, is equivalent to minimizing a special type of loss function over the training set. This loss function is called a logistic loss. So they are doing the same thing. So this is just another example to show how the Bayesian learning and non-Bayesian learning are well connected. So some probability likelihood and corresponds to a particular type of loss function. Any questions so far? This is a loss function. This loss function is defined like in this way. So you can define any loss function as long as it can well represent or well reflect your belief how well your training exam your prediction would fit the data. And this is one way to define that. Of course, you have other way like hinge loss, right? Or 0-1 loss. But here we can choose another definition, which is called logistic loss. And later we'll compare those different loss. We actually have a loss zoo, right? Different losses and how they're, if you place them together, you'll find some interesting things. Any question? Okay, so here's about maximum likelihood estimation. We have arrived at our objective, right? So now I want to extend it to maximum A posterior estimation. Right? As we mentioned before, maximum A posterior means that we want to consider the prior of the model parameters, right? For maximum likelihood estimation, we don't have any prior preferences over different parameter choices, right? But for maximum A posterior, we do have. So we need to encode our beliefs or preferences over the weights with some prior. Right? And there are a lot of choices. Those choices are really depend on the user, right? Depend on you. Right? But here we just want to introduce a very commonly used prior, which is called Gaussian prior. So what does Gaussian prior means? Just means okay, we believe in a prior distribution. Each weight in our weight vector is drawn independently from the normal distribution with 0 mean and some standard deviation sigma here. But someone asked why should you choose 0 mean or some standard deviation? Why don't I choose mean to be 1 or -1, something like that, right? There's no like you must do or something like that. You are free to choose whatever. But this one is some kind of common use ones. And it works pretty well in many applications. So in practice, if you want to add some prior, you can start with that. Right? Unless you have some strong evidence, empirical evidence showing that I should choose other priors. Right? So now from the our discussion about maximum likelihood estimation, right? We know this is our likelihood of the data, right? Given the model parameters. And we also have our prior, which is defined as the independent Gaussian distribution, right? With 0 mean and some standard deviation sigma. So if we want to construct, we want to find a map estimation, right? As we discussed before, we really do not need to compute the full posterior, right? Because the posterior is proportional to the prior and likelihood. So if you want to maximize, this posterior probability, you just need to maximize the product of the prior and likelihood, right? And again, we want to do this in a log domain. So we take a logarithm, which is equivalent, right? We maximize the log likelihood here plus a log prior. That's it. Right? So you can see that as compared with our MLE estimation, right? we just add a log prior term in the objective function, nothing else. Okay. And this is our log likelihood term, right? Log, which is this, right? We have already derived, right? So if we further expand the log prior, so you see that this is actually the individual or independent Gaussian distribution. If you take a logarithm over this bunch of stuff, right? And you know, this term has nothing to do with W, right? It's just something constant, and log exp they cancel, right? So actually, you'll find the log prior is a summation over each weight, where each summon is minus Wi squared over sigma squared is the exponent term, and then plus some constant. So now you get our objective for the map estimation. It's pretty similar to the MLE estimation, right? The only thing is that you actually add a bunch of square terms over individual weights, right? Any questions so far?
Example that the items is not independently and
yeah, that's there are a lot of examples. Like for example, a very commonly used I mean, non-independent prior is like something like for example, I want to predict, give me a gene profile. If you screen your gene expression level and want to predict if this guy might have a tumor or not, right? I can formulate as a logistic regression problem. But the problem is that I want to know, because many gene segments, they have like close related functions. So that means that I want to know which particular groups of the genes will be really effective to predict if that guy has cancer or not. Then we should put some another prior where we either encourage the whole group of the genes weights are activated or not, simply zero. In that case, this is not like Gaussian prior. It could be Laplace prior, or it could be the group Lasso prior, or like group spike and slab prior. A lot of choices. But if you don't want to like preempt a bunch of weights and select only a subset of weights, well, maybe this individual Gaussian prior is the easiest choice. Other question? Likelihood won't be changed, because likelihood it's actually likelihood is the uniqueness. It is a uniqueness of the model, right? If you choose another likelihood, then you wouldn't call this logistic regression, right? Because you use logistic function or use Sigmoid function to make the prediction. If you change the likelihood, it might be other models like linear regression or artificial neural network. But prior, you have a lot of choices, actually. Okay. So again, we have a minus sign here and minus sign here, and we do this maximization, and it looks awkward. So we can just cancel this sign and then change it to minimization, right? So maximizing a negative function is same as minimizing the function itself. Right? We arrive at our final objective, right? We essentially to minimize a summation of logistic loss over the training data plus some regularization term, right? Remember, this is a regularization term. this regularization terms also appears in SVM, right? So this actually links back to the loss minimization principle we have discussed before, right? So we said that in the regularized empirical risk principle, right, we should define our objective function as two terms. First, the training loss over the entire training data, right, which describes how well your model fit the data, right? But you should also add a regularization term which penalize over complicated hypothesis space. Right? And if we do the map estimation, do some kind of simplification and deduplication, right? You actually avoid the same structure in the final objective. Yeah, and this kind of linkage almost appears everywhere in the Bayesian learning and also non-Bayesian learning. So now I want to give some hint to compute the objective function, compute the gradient of this objective function, because it will be required in your implementation of the logistic regression model and also in your homework. We want to showcase how you apply the previous results about sigmoid derivative to simplify the computation. Right? So I'm gonna switch to the iPad. Oops. Okay, hopefully it looks a little bit nicer. Oh, maybe, yeah. So this is our final objective for the map estimation for logistic regression, right? So if you want to compute the gradient of this objective function to conduct a gradient descent training or stochastic gradient descent training, of course we need to take the gradient of each loss. Okay? And this gradient is really easy. It's just 1 over sigma square and W, but you have to multiply 2 here, right? Because W transpose W. But here, how do we compute the gradient of this? Right? Any suggestion? Yeah, of course we use chain rule. So we need to reuse our definition of sigmoid, right? So we know that sigmoid is 1 minus 1 plus e to the power of minus z, right? So if you take a look at this is essentially minus log 1 plus this guy minus 1, right? If you move this minus 1 to the front, it cancels minus in front of it, right? So this guy is a sigmoid, right? Right? So actually your logistic loss is essentially, for each example I, is essentially minus log sigmoid yi w transpose xi, right? So now, if you want to take the derivative of this, let us see how the trick is going on, right? So apply the chain rule, it will be minus, like you divide 1 over sigmoid, right? This is for sure. It's just choice. How do you take the derivative for log function? And now you take the derivative of sigmoid. What's that? this guy is sigmoid times 1 minus sigmoid, right? So now you can see that you can cancel the sigmoid both in the numerator and the denominator, right? And then you apply the chain rule here. You just calculate gradient of this guy, which is just yi xi, right? Because it's just a linear term. So you can see that the form of the derivative is really simple, but you need to know where to apply the trick we discussed before. Right? So the derivative of this guy, right, is simply minus 1 over sigmoid yi xi. Does it make sense? Right? Don't forget to apply that. Otherwise, you'll find, okay, it's why is it so disgusting to compute the gradient? Okay, and then let us look at how do we conduct stochastic gradient descent training for logistic regression, right? So it's very similar or exactly the same as what we have done for the SVD stochastic subgradient descent for SVM, right? So I just write down the algorithm framework. First, you're gonna initialize your W, right? And you can initialize them with 0 if you like, right? Or any other random numbers if you like. Don't worry, because the objective function here is convex. So you don't need to worry. You don't need to like in neural network. We don't recommend to initialize with 0, but for logistic regression for SVM is okay, right? And then you're gonna go through like big T epochs, right? Each epoch meaning that you're gonna go through the data once, right? So inside each epoch, you first do the random shuffle, and then you look at each training example. Xi, yi, right? Sequentially. And then because we're conducting stochastic gradient descent, right? So this is something we should be aware, right? This is something like because the full objective is the loss plus some regularization term. So once you treat this particular example xi, yi as whole data set, you need to duplicate it for m times. Then as this regularization term, you calculate gradient. That's a valid stochastic gradient. So this is the same as what you did for the SVM. Why? Because we have an extra term. You have to ensure your stochastic estimate of the loss match the skew of the exact loss here. Right? So your gradient will be like some learning rate will be something like that, right? M times logarithm 1 plus exp for minus yi w transpose xi n plus is 1 over sigma square w transpose square. Right? You have to duplicate. This is very important. You have to duplicate this particular random sample for m times so that your stochastic estimation of the loss, right, have same skew as the original loss. Then your gradient, this is called stochastic gradient, will be unbiased. And then you just update, and maybe you should update gamma t, right? Because gamma t if you want to ensure your training to converge, right? You should ensure their gamma t to satisfy like two properties we discussed before, right? So you can use the schedule we introduced in your SVM, right? Like 1/1 plus gamma t or something else, right? As long as they're kind of decreasing, their summation is divergent, but the square summation is bounded. Right? And then you go to the next example, and you find the next example. You duplicate them to match the same size original training set and calculate the stochastic gradient, and you update W again until you finish the whole training epoch, and then you go to the next epoch and do the random shuffle and repeat this procedure, and finally you're gonna return your learned W. That's the whole procedure. Any questions so far? M is the total number of training examples. Yeah. Yeah. This is, suppose this is your whole training data, right? You have M pairs of the training input and the label, right? So when you're doing a stochastic gradient descent, right? Every time you only deal with one example, right? But if you want to compute the stochastic gradient descent, stochastic gradient, you're gonna duplicate this example for M times so that you can view like the duplicated example, your fixed data set has exactly the same size as the true data set. Then you just construct the objective on this fixed data set, right? Which will be M times your logistic loss plus this regularization term. Then you take gradient. Any question? Yeah, this is exactly the same what you have done for SVM, except that in SVM here, we replace this guy as some hinge loss, right? Okay, hopefully this helps clarify how to conduct the training of a logistic regression. So now let us go back to the let's go back to the slides. Right? Oops. Yeah, so now I have finished the discussion about how to train a logistic regression model. Right? So the final few things we want to discuss is the linkage of this loss minimization framework. So here I want to give a more detailed and comprehensive review of the loss minimization principle. Right? So the general setup is as follows. So assume our training examples X are drawn from a fixed unknown distribution D, right? We know that is some complicated data distribution, which we don't know how it should be, how we should write down its probability density, right? And we also assume there are some hidden oracle classifier. Okay, one second. Oh, sorry. I should share this again. Can we see that? Okay, great. So, and we assume there are some hidden oracle classifier, right? the ground truth or concept, whatever, F, which give the exact labels, right? And we wish to find a hypothesis H that is close to F as much as possible. Right? So the ideal situation is that we're going to define a loss function, L, that can penalize the bad hypothesis in a hypothesis space so that we can find the best hypothesis, right? So in general, we can define our objective function in this way. So it is an expectation, right? Expectation over the data distribution and of the loss for any training input comes from this data distribution. This loss measures the difference between the prediction made by its particular hypothesis and the ground truth, right? However, because the data distribution D is really unknown, right? We cannot write down the exact form of this expectation. So in practice, we're going to instead just draw a bunch of examples X, right? Like 100 or 1,000, even 10,000, right? And then we just average over those, average the loss over each training examples as our final loss. This is called empirical loss. So we can view this average over the training examples as approximation or estimate of this expectation, right? So if you view this one, this guy is a random variable, right? It's a random variable of the X, right? If you want to estimate this expectation, how do you do that? You just sample a bunch of instances of the random variables, just average, right? And you get your empirical loss. Any questions so far? Is there everyone comfortable with this? Well, imagine like if you want to do the image classification, right? So your data set comes from all kinds of images generating by internet, right? But how do you write down the distribution of the images? It's not Gaussian, it's not TD distribution, it's not whatever distribution we have known so far. It's actually very hard to know what the exact distribution is. We can collect them, we can get their samples, right? But it's very hard to write down the probability density function of the images, right? It's actually the most cases in practice. Right? You can collect data, but you don't know which specific function which governs the generation of data. Okay, so and if we conduct our learning by minimizing this empirical loss on the training set, this principle is called empirical risk minimization. But there's a problem here, that is overfitting, right? If you have because it only cares about the loss or the accuracy on the training set, it is easy to lead overfitting. So to address that problem, we want some kind of term to penalize complex hypothesis, which is called regularizer, right? So if we add some regularizer to our training loss, and then we minimize this whole function or objective function, we call this principle as the regularized risk minimization. So regularized risk minimization, to conduct that, you have to define two terms. One is the regularizer. How are you going to penalize complex hypothesis, right? And the other is the training loss. How do you evaluate the goodness of your model fitting the training data, right? So two things, right? So for the linear classifiers, well, you can use L2 regularization, right? This is what we have done for the SVM. And then you have a hinge loss here. Right? But in general, what is the ideal loss? In general, ideal loss will be, okay, if I make a correct prediction, I don't suffer anything, right? I don't have any loss. My loss is simply zero, right? I only need to have some loss when I make wrong prediction. Say the loss is simply 1. if you don't have any preferences over the importance of training examples. I assume as long as I make a wrong prediction for any example, I'm gonna have a loss 1. Right? So this is called a 0-1 loss. So 0-1 loss is kind of like ideal loss in a theory sense, but we'll never be able to use that in practice. Why? Yes, exactly right. So if you look at 0-1 loss, if you define 0-1 loss for the linear classifiers, you see that it's just a step function, right? So you actually don't have a gradient. Right? So it's very hard to even use the subgradient. That subgradient is really, really inefficient to optimize it. So it's very hard to optimize that loss. That's why in practice people rarely use 0-1 loss. Right? We always define some more smooth, more easy to optimize surrogate. Right? So we actually have seen many loss functions, like perception loss. Right? We discussed, right? When we talk about the SVM, right? When we talk about actually the perception is also doing some stochastic subgradient for some loss function. Right? So it's called perception loss. The hinge loss is for SVM. For eta boost, this is actually the exponential loss. And in logistic regression, we discussed today is called logistic loss. Right? So if we put all those loss functions together, we have a zoo of loss. Right? So you can see that this guy is the ideal guy, right? Ideal one is called 0-1 loss, but it's very hard to compute during training. So people have developed a variety of different surrogates, right? Hinge loss, SVM, essentially is an upper bound of this 0-1 loss, right? And perception is something like that. It's kind of like overlaps with or intersects with 0-1 loss, right? And this is a eta boost loss, right, which is another smooth upper bound of the 0-1 loss. And here's our logistic loss, right? Yeah, we have finished our introduction of logistic regression, right? So to summarize, logistic regression is a classifier that predicts the probability the label is 1, rather than just give you the label. Right? So it is a discriminative classifier that can be trained while either MAP or MLE estimation. And to conduct the training, we essentially minimizing a logistic loss over the training set. Of course, if you're doing map estimation, you add some regularized. Okay, let's stop. Let us stop here today.